All right, so we're going to talk about surfaces of revolution today. Okay, let's get started, folks. So far we've talked about several special kinds of surfaces. We've talked about spheres. Spheres are nice and easy. We talked about planes. Planes, nice vectors. Deal with vectors with planes. We talked about cylindrical surfaces. And we talked about quadric surfaces. And we will work with these a lot more as we move forward. We just have kind of an introduction to most of these. We worked with planes a fair amount. The cylindrical surfaces and quadric surfaces we'll work with quite a bit as we move forward. We want to talk today about another special type of surface. So surfaces of revolution. So we'll have 5 special cases of surfaces that we'll deal with. And then as we move forward, we'll get to lots of different kinds of surfaces. But these are nice ones that we can deal with fairly easily. So what we're going to do for a surface of revolution is we're going to look at everything okay there? I didn't think there'd be any trouble. I didn't see any tape today. We're going to look at a curve. So we have some curve, and we're going to say our curve is in the for this particular to do this particular development. We're going to say our curve is in the YZ plane. So we have some curve in the YZ plane. And I'm going to call this function in the YZ plane y equals r of z. And the reason I choose r will be clear in just a second. So y equals r of z in the YZ plane. And we're going to revolve this curve about the z-axis. And we're just going to look at one point on this curve. So we're going to revolve about the z-axis. And this point in space, the coordinates are 0, r of z, z. Now when I rotate this when I revolve this curve about the z-axis, what path does this point take? What kind of path? Circle. This is going to travel in a circle about the z-axis when I revolve that around. So the point moves in a circle. And the equation, so it's going to be a circle parallel to the xy plane, and the radius is its distance from the z-axis, which is r of z. So the radius is r of z. So the equation of this circle is going to be x squared plus y squared equals r of z squared. And that's going to be true for any point on this curve that we rotate around. The equation of the circle that point makes is going to be given by x squared plus y squared equals r of z squared. Well, this gives us our equation of our surface. So each point on the curve makes a circle about the z-axis. So, and the equation of the circle is given by this equation. Well, that's our equation for our surface. So what we're going to do is generalize this argument for each of the three axes, and we can come up with the equations for surfaces of revolution about any of the axes. Does this make sense what we're saying here? So we're going to generalize this. So we get three cases. Whoops. So if we have a surface of revolution about the x-axis, the form of our equation for our surface of revolution is going to be y squared plus z squared equals some r of x squared. Some function of x that gives us our radius of our circle. And if I want to talk about the y-axis, I get x squared plus z squared equals some function of y squared. And then we already talked about the z-axis. That was the case that we used because it was easy to visualize. We get x squared plus y squared equals some function of z squared. So these equations give us the forms of the equations for surfaces of revolution about our three coordinate axes. So this just gives us another way to work with surfaces, to think about surfaces in three dimensions. So what we want to do is look at a couple of surfaces of revolution, and then we'll kind of go the other direction. We call before we go on, we call the r of x, r of y, and r of z, we call those the generating curves. So those are the curves that generate our surface of revolution. All right, so let's look at a couple of examples of surfaces of revolution, looking at the surface of revolution, and then we'll talk about finding a generating curve from a given equation. All right, so let's say we have we want to revolve, we want an equation for the surface. And we're going to form it by revolving z equals the natural log of y about the z-axis. And we have some familiarity with surfaces of revolution. We know how to find the surface area of a surface of revolution. We know how to find the volume of a surface that's formed by revolving a curve about an axis. So this just gives us another way of working with these things. All right, so we want to revolve this curve about the z-axis. So because we're revolving about the z-axis, we want our radius function, we want our generating curve to be some function of z. So we want our radius to have the form we want a radius to be a function of z. So we want some r of z. So how are we going to get a function of something with a function of z for our radius function? What can we do here? Any ideas? So we're going to need y. We're going to need some function y as a function of z or x as a function of z to get our generating curve. Can I do that somehow? Derek says no, it's impossible. I can exponentiate both sides. So if I exponentiate both sides, I get y. Exponentiate, yes. Y equals e to the z. So there's y as a function of z. There's my function of z. And since we're revolving about the z-axis, my equation is going to be, and this is going to be my r of z. So the equation of my surface is going to be x squared plus y squared equals e to the z squared. And I can write x squared plus y squared equals e to the 2z. Too easy? So let's take a look at what this surface is going to, let's look at what the surface is going to look like. So draw our axes here. This is my favorite part of all of these surfaces, is thinking about what they're going to look like. So in the YZ plane, my graph is y equals e to z. So what is my graph going to look like? Or we could also grab z equals natural log of y. So z equals natural log of y. Let me extend my z-axis back. I'll extend my x-axis to the negative direction here. So z equals natural log of y is going to look like this, right? Something like that. And we're going to revolve this about the z-axis. So if I revolve this curve is going to go in a circle, like so. So over here on the other side, I would get the same curve in this plane. So we get this kind of infinite funnel shape. So there's the circle it makes in the xy plane. So yeah, like the bell of the trumpet, except extending infinitely out. That would be a really loud trumpet. Except the mouthpiece down here would be really, really small, so it'd be really hard to play. So that's what our surface would look like, this kind of funnel with an exponentially shaped side. Questions on that example? And then we also we would know how to, hopefully, find the surface area of that surface given some bounds on our curve, or the volume given some bounds on our curve as well. So we've done that. We've worked with surfaces like this before. All right, let's look at another example. We want to revolve eight x squared equals y to the third about the x-axis. And we want the equation of the surface of revolution for this surface. The surface generated by revolving that about the x-axis. So we want, when we revolve about the x-axis, we want our radius function, our generating curve, to be a function of x. So we need some r of x for our radius, for our generating curve. So in this case, what are we going to do here? Divide by 8. Take the square root. So we're solving for x. Do we want to solve for x? We want to solve for y. So we want a function. We want a function of x. So we want y in terms of x. So we get y equals 2x to the 2/3. So that's going to be our radius function. That's going to be our generating curve. So this is our generating curve, and since we're revolving about the x-axis, we're going to say y squared plus z squared equals 2x to the 2/3 squared. And that would be the equation of our surface. And I can simplify this if we want to. Well, let's figure out what this thing is going to look like. So we're going to sketch our surface. This one's a little trickier. Let me see how I want to do it. I'm going to draw my x-axis kind of out this way, and my y-axis down this way, so it's a little easier to see. So in the xy plane, what kind of curve is 2x to the 2/3? What does that look like? Kind of like a square root or a sideways parabola. So in the XY plane, it's going to look something like that, more or less. And then we're revolving that about the x-axis. So this would go in a circle about the x-axis. So roughly that's what our surface is going to look like. So this is y equals 2x to the 2/3. And we revolve that about the x-axis. Not necessarily a perfect sketch, but it gives us an idea of what the surface looks like. So questions on that one? All right, so the other thing that we want to be able to do is go from an equation of a surface and find an equation of a generating curve. Now I wanted to point out something here before we do that. Is y equals 2x to the 2/3, is that the only generating curve I could have come up with for this surface? Davis says no.
Could have come up with the one on the other side, or anyone that's around the outside.
I could, right, so we could go with the equation of any curve that forms the edge of the surface. So I could go with this curve in the xy plane. I could go with a curve in the xz plane. I could go with a curve in the negative xy plane. So any of those curves would be a generating curve for this surface. And we would still be revolving about the x-axis. So the generating curve is not unique. So I could go with curves in any of the planes that form the boundary. So for example, if I looked at the curve in the xz plane, if I looked at, let me write it in red here, I could have gone with that as the generating curve in the xz plane. So I could have said z equals 2x to the 2/3 would work as a generating curve as well, and revolve that about the x-axis. And like Davis said, any curve that's along the boundary of this surface would be a generating curve. All right, so now we want to go the other direction. Now we want to be given the equation of a surface, we want to find a generating curve for a surface of revolution. So let's look at this again. So we want to find the equation of the generating curve. And we have x squared plus z squared minus 3y squared equals 0. So before we start, let's think about what we have here. Think about what we've learned already. What kind of surface is this? Not just big picture, not specific. What do we call this kind of surface? Our equation is a second degree equation in each of the three variables. So what do we call that kind of surface? This is a quadric surface. So because we have a second degree equation in each of the three variables, this is a quadric surface. So we can think about the surface in two different ways. We've talked about this as a quadric surface, where we can also visualize it as a surface of revolution. So what we want to do, we know that our surface of revolution has the three forms. X squared plus y squared equals sum r of z squared. Y squared plus z squared equals sum r of x squared. And what did I miss? X squared plus z squared equals sum r of y squared. So we want to put this surface in one of those forms. So I'm going to just rewrite this. X squared plus z squared equals 3y squared. So just looking at this form, what I can think of this as a surface of revolution. What axis am I revolving this? Is this surface of revolution being revolved about? About the y. So we're missing here we have each of these to the first power. So that's this. We can think of this as the equation of a surface. So we are revolving about the y-axis. So this 3y squared is going to be our radius function. So r of y squared is 3y squared. So our radius function, our generating curve, r of y, is going to be square root of 3y. Now we just need to find the equation of our generating curve. What would give us an equation of a generating curve that's this square root of 3y? So thinking about what we talked about with the last problem, we're revolving this about the x-axis, so we can think of our curves being in which planes? Or sorry, revolving about the y-axis, so we can think about our curves being in which planes? Let's draw a picture over here. So it helps you visualize. Draw a picture. So we're revolving about the y-axis. So what planes would be convenient to have our generating curve placed in? If we're revolving a curve about this axis. The xy or the yz. So if I have a curve in the xy plane, some curve down here, something, I could revolve that about the y-axis and get a surface of revolution. Or I could put my curve in the yz plane, revolve that about the y-axis, and get a surface of revolution. So if we want this to be our generating curve, what are going to be this to be our radius function? How can we write our generating curve in the xy plane or the yz plane? How about x equals square root of 3y? That work? How about z equals square root of 3y? Either of those will work. So that's going to, either of these are going to be a generating curve. So in the xy plane, what kind of curve is z equals square root of 3y? It's a line. And our slope is square root of 3. So so we're going to get something. I'm just going to draw a line here. There's our line. If we rotate a line about the y-axis, what kind of shape do we get? A cone. We get the same line in the xz plane. So we get, and my drawing isn't great here. Let me redo my drawing a little bit. So we get a cone. And this also, we could also extend this line in the negative direction, back this direction, and down this direction. And our cone has two parts, because our line can extend through the axis there. So we call these cones a cone. This is called a double naped cone. And we could also think of this, if we thought of this as a quadric surface, to get a cone out of the quadric surface, what I would say is in the YZ plane, I let x equal 0. So the equation in the YZ plane is z equals plus or minus square root of 3 times y. So I get a line in the YZ plane. In the XY plane, I let z equal 0, and my equation there is x equals plus or minus square root of 3 y. So I get lines in those two planes. That's going to be the sides of my surface. Those are going to be the traces of my surface in those planes. And so the traces are lines. So my surface is a cone. Questions on that example? As we get more experience with these surfaces, visualizing them will get a lot easier. Like I said the other day, by the end of next semester, we'll see this equation, and hopefully we'll know immediately that's a cone. That's a cone, and our axis is the y-axis. That we'll use these enough that you'll be that familiar with those surfaces to look at this equation and say, oh, that's a cone, and the axis is the y-axis. All right, questions? Tranya? Little sip? Tasting okay? Just tiny little sip? But that was the point. It seems terrifying, but it really isn't.
No, that's a little terrifying. Nothing to do. What was most terrifying is love.
Yeah, the lava
Yeah.
controller.
I save that for my private moment, when I laugh like that. All right, our homework today. Sometimes when I'm grading your test. No, and then there are other times I have to stop because I'm afraid the tears will stain the test. But that's few and far between.
I think that's been my test usually.
I have the other copy all over copy. Me too.
Oh, okay. Got it. I think I get that.
Probably.
All right, there you go.